Goedemiddag Utrecht. Bedankt voor het kiezen van deze sessie. Welkom bij C# Interceptors. AOT and performance for free. Let's do a bit of a cold open. I have here some C# code where we print out interceptors. Then I'm invoking here this static method with hello world. I would expect then this method is called, so to print ordinary method together with hello world. And in the second line, I create an instance here and call an instance method, which now should go down there to ordinary method and then print FutureTech 2025. Now, if I run this, do I get these ordinary methods from here? I do not, because these methods actually are not called, they are intercepted. And in this session, we'll figure out what that means and what we can do with source level interception. Hello world, I am Stefan Pölz. I'm from Austria. I'm a Microsoft MVP, a JetBrains community contributor, and a co-organizer of the .NET Devs AT, which is a local .NET user group in Vienna. This QR code links to my GitHub page. If I'm also listing my social media there and my live streams. So if you have any questions about interceptors that I cannot answer today, then please reach out to me and I sure will figure out the answer to your question. All the demos that I share are also on GitHub. At the end, I will share a link to that repository as well. Now, what are C# interceptors? So which methods do we actually call here? If I set the breakpoint, I would expect to jump down to the static method. But if I now step into this static method call, we actually jump to a different method. Now this method has a different name, but it does have a matching signature. It still takes a string and still returns a string. And this method is attributed via this attribute, the intercepts location attribute. Now this is still an earlier version of interceptors that I'm showing you here, but they're very cool to show for demos. But they are now deprecated since just a month ago. Now the stable release has been out of interceptors. They look slightly different, but I still wanted to show you the older version as well, because there's still a lot of content for the preview feature, because this has been for a couple of years out there for us to experiment with. So how does this interception really work? Who has written, at some point of time, a goto? I see nods and a couple of hands. Excuse me? So let's say I have here, I want to print a skipped and also an executed. But I want to skip over the skipped, so I can do a goto. I want to go to a label with a specific name. Let's call this label label, and let's give the label here. And what is happening when we hit this line, we go to wherever this label is and continue execution. Let's see if it works as expected. So we should only see executed, but we don't see skipped. Now an interceptor is kind of a bit of the opposite. It's more of a more of a come from. So we don't dictate to go to a specific line of code, but we say, hey, whenever we hit this specific line of code, please come to me. And this specific line of code is actually here after the dot. This is the invocation of the method. From a Roslyn perspective, this is where Roslyn understands, okay, this member, this static member is invoked here, so this method is called. And this location is at line 7, position 35. If we go to this interceptor, again, that's the preview version of it, this intercepts location attribute, well, this does not exist in the BCL. This is an attribute that you have to create yourself. in order for this feature to work. So interceptors isn't, strictly speaking, a C# language feature. It's more of a C# compiler feature. So the Roslyn compiler, when at the time at binding and understanding, okay, which syntax is calling which method, this is then where interceptors are resolved and potentially some routes, some calls are rerouted. So the compiler does a little sleight of hands there. And you have 3 arguments: the file path, the line, and the character where we want to come from. So which call is intercepted. Now the file path is indeed the physical file path on disk, because this source level interception that happens at compile time. And the column and the line number. So in here we then understand we want to intercept this call and reroute it to here. Same happens with the second method, where we now are still in the same document, but on line 8, character 42, and that's again after the dot, we are at character 8, line 8, character 42. But this time it's not a static method, but an instance method. And in order to intercept instance methods, well, we write something that is very similar to an extension method. Or it actually, well, it is an extension method. So we extend this instance, that's the receiver type, that we want to, the instance method that we want to intercept, and the same number and types of arguments and the same return type, and then it's good to go. This interceptor method needs to be accessible from the intercepted location. So this is internal here. If I were to make this private, this method, well, the name is different, but just the signature must match. The name does not. Is no longer accessible from this call site here. So if we were to build this, we would now get an error at compile time and saying that this interception cannot occur because the interceptor is not accessible. When we have interceptors, well, this attribute that doesn't exist in the BCL, usually we make as a file local type, so that it doesn't clash with other sources where this attribute is coming from. We will learn later on that source generators are the main producer or the exclusive producer of interceptors. So we have 7 different generators in our project, and all of them are emitting this attribute because a generator cannot depend on another generator. We don't want them to mess each other up. So it's always a good practice to have file local types, as well as this intercept, the class that contains the interceptors. Usually you can also make file local. File local doesn't mean it's not accessible from outside. Perhaps you have seen this when we jump to SharpLab. When we have a file local type, that's usually the name gets mangled so that we cannot really speak it anymore outside of that file. So if I were to create a new C here, what's really happening under the hood is that this file local type really is an internal type, but the name is mangled. So we can really only speak of it with user code from the file itself. But generators via this attribute, they are happening later on in the binding phase. They still work just fine. I just recently learned, I thought that this come from, actually was just a joke, some esoteric, but this actually is implemented in the C intercal, and also Python seems to have implemented that as well. I should definitely check out Python, how they are solving that. Or maybe not. And yeah, there are some more rules that that are for source level interception. I'm also listing all the documentation. You can go to the documentation page that is listing all of the rules. For example, currently we can only intercept ordinary methods. Now, what is an ordinary method? If we jump in a different solution here, I'm writing actually a source generator. So we're writing some Roslyn components here. Sorry, my tool has stopped working. There we go. So there's actually writing a source generator. So we're in the context of Roslyn. There is an enum called method kind, and there is a member called ordinary. So we can take a look at which methods are non-ordinary. For example, the getters and setters of properties. Once compiled, they really compile into get and set methods, but these are not ordinaries. Properties cannot be intercepted. Also, user-defined conversions or operators, things like constructors, and a lot of other non-ordinary methods currently cannot be intercepted. This may change in the future. Now, what is the history of interceptors? I mentioned I was talking a bit of the experimental phase. So initially, this interceptors experiment was added in the .NET 7 in the final feature band release of the .NET 7 SDK, but also during the preview of the .NET 8 SDK. And this is where the compiler started to respect methods that are annotated with this intercepts location attribute that the tool has to emit itself. And then we have to opt in to this feature via this MS-build property in our CS project files. This was later on changed to be more explicit and actually specify the namespace of where the interceptor is in. So in our example, where we actually have source level interception going on, if we jump to the CS project, we see that in this interceptors preview property, I know that this source generator's demo generated namespace. And this is exactly the namespace where the methods, where the interceptor methods live in. Since source generators are meant to emit these interceptors, they're not really meant to be written by user code. It's good practice that each generator emits its interceptors in a separate namespace. So again, that it doesn't clash with others, and we may or may not explicitly state that, hey, we are aware there is interceptions going on. So to keep our code base somewhat sane, not just to reroute any method and we're not really sure anymore what is going on. And during the preview, this feature has now later evolved. So with the last release of the .NET 8 feature band, we got now a new attribute that looks similar like the previous one. In the earlier one, we had the file that we want to intercept at, the line number, and the character position. Now it's two parameters. We have a version. Currently, the version is just version 1, and a data string. And this data string encodes all of the information, like the source file that we want to intercept, also the position that we want to intercept, and also some additional debugging information for error reporting. And this is also the attribute that is now in the stable release. So when you create or when you see interceptors, you will very likely now see this new version of the attribute. If you see the older version that takes three arguments, this may be in the future deprecated and may no longer work. You actually get warnings when you use the latest .NET SDK, because since 9.0.200, which got released pretty much a month ago, or exactly a month ago, since then interceptors are stable. And in order to opt in to the interceptors, we no longer have interceptors preview namespaces, but just interceptor namespaces where we state the namespaces where we have interceptors in, and using this new attribute. The rest of the design is largely the same when it comes to the rules of source level interception with which how it was in the earlier preview phase. So what can we use interceptors for? I mentioned two things: AOT, native AOT, and performance. Let's start with the performance aspect. if we consider this benchmark, I'm writing a benchmark with benchmark.net. Who is familiar with benchmark.net? I see almost all hands, which makes me very happy. It's an amazing tool. I use it all the time. I shouldn't use it all the time, but I need my fix. So what I'm having here, I'm using the string comparison enumeration that has this 6 values, or this 6 named values. And I'm then having 2 benchmarks where we get the name of this constant here. One is using the BCL version. So this is not intercepted. This is really calling into the BCL version of getName, which works with each and every attribute on this planet. Sorry, with each and every enum on this planet. But also, I'm emitting a very special case interceptor that is working exclusively for the string comparison enumeration. Now, when we have a source generator, I'm doing this here in Rider. In Visual Studio, the experience is very, very similar. We can go to our dependencies. In Rider, we can go to source generators. In Visual Studio, it's not under source generators, but it's also, you find it under dependencies, where you then find the package of where the generator is contained in. And this generator here is emitting, again, at compile time, now an interceptor. Again, this attribute does not exist in the BCL, so we have to emit it ourselves into the source code. Still using the old version here. Later on, we will refactor it to the new version. And here is now the new getName method. Again, it's the compatible signature, because the intercepted call here is taking a string comparison and returning a string, a nullable string. And compatible signature, we take the string comparison and also return a nullable string. Again, the name of the interceptor method does not need to match with the intercepted method. This is where we then have the exact location of the invocation where we want to intercept at. So again, in this case, this would be exactly here in this document, line 41, character 25. Here it is. And this now actually is emitted by a source generator. So if I were to add 2 lines here, now this is no longer line 41, but it's now line 43, and the source generator has happily updated this interceptor for me. And this is now the getName implementation that only works for string comparison. And if we take a look at the benchmarks, we see a difference. It's a tiny difference, but a difference all the same. So I'm definitely not stating that the BCL is slow. Actually, over the last couple of releases, the enum members got faster and faster. When I started with writing this generator, there was still a more significant difference, but the .NET team's done an amazing job to optimize it. But still, we can see a difference of emitting a special case method that only works for this one specific enum, and the general purpose that works with each and every enum. We could do something very similar with the isDefined method of the enums. Basically, the very same benchmarks, but just with isDefined, which takes an enum and returns a Boolean. And the source generator is now emitting a compatible interceptor method that is attributed with this attribute, and then there's a very special case implementation to return whether this value that we give in is indeed, in this case, between 0 and 5 inclusively. And again, the performance will be, well, it is sub-nanoseconds, so barely measurable, but it is a little bit faster. So performance is one big use case of source-level interceptions. And it's also for free, because I don't have to write this code. well, I have to write, or somebody has to write the generator, which is emitting this very special case implementations. But I now, as a consumer, I just can start writing the very same C# code as I used to be, and my code will just get a little bit faster. Now my call sticks, if some errors occur, they may look a little bit different. So it's always good to be aware of where interceptions are going on. And usually when taking a look at the CS project, we should then find here where namespaces are that contain interceptors. The second use case mentioned, Native AOT. Who has heard of Native AOT already? I see roughly half the room, not quite. Who of you has already tried out Native AOT, compiled and published something with it? I see 7 hands, and then 8. Cool. So what is Native AOT? When we compile our code, please take a look at the upper half. Usually what we have is our input, which are our C# files or Visual Basic files in our C# projects, additional MS Build properties or targets, and maybe also some additional files like some property, some JSON configuration and such. We sent all of that to Roslyn, where Roslyn is now creating syntax trees out of the C# files and creating a compilation, also doing source level interception at that point. And then it spits out IL, intermediate language. The cool thing about intermediate language, it runs everywhere where .NET runs. So in this stage, we don't really need to know at which machine our, for example, DLL or our executable is running on. Not at the time of publish. Later on, when we then start this application, for example, on a Windows 64-bit machine, now this is where the JIT comes in, the just-in-time compiler, hence the name, which now takes the IL code, and just as we start this application, is now converting this IL code step by step into machine-specific code that is actually executable on this very machine. And the JIT has also now various stages. So at the beginning, it emits code super quick, and if a method is called many times, it then rewrites it into faster code. So the JIT is an amazing beast. But there is still a little bit of an overhead, because we are not ready to run. We first need to compile our IL code into machine code. For example, for hyperscaling scenarios, when we have small services that we need running in an instant, or close to an instant, this is now where we could use the AOT toolchain. Again, we have our very same sources, but now at compile time, we not only compile our code to the IL representation, we also apply trimming and linking. This is stuff that we could also, the trimming part, we could also do in the just-in-time scenarios to reduce the size of our outputs. So trimming is some sort of tree shaking where we get rid of methods and types that we're actually not calling in our user code. And then we again apply the JIT. But then at the time at the publishing, so at publish time, we now have the executable. And this now is ready to run. This already contains machine code. So all we need to do is run this on the target machine. So this is not portable. We need to publish for the target architecture. But since there is no JIT and the code is ready to run, we will notice a startup difference. But with this faster performance, with this faster startup performance, comes also a bit of a drawback, because the just-in-time compiler can also, in our source code at runtime, we could emit new IL code still at runtime of our application that then gets just-in-time compiled while we are running into machine code. One of these examples is regex. Let's take a peek at the regex implementation. Again, I have a benchmark here with a simple pattern just to detect, is this a C# or a Visual Basic file? I have one static regex here that is also using the compiled flag. this compiled flag is the first time this regex is run, new IL code is emitted, special case for this regex, so that subsequent ones are as fast as possible. That means that the first time when we invoke this regex, we will notice we notice an impact. It will be slower than the interpreted version. But every subsequent one will be faster. So if this regex is called more than once, it will pay off sooner than later. So I have one benchmark where I, super inefficiently, but just to show some differences, create a new regex every time, not compiled, and just run it. So this is using the interpreted version of regex in .NET. Having the same example, creating a new instance with the compiled version. So this is definitely a bad pattern because we pay this impact on the first run, but then discard this regex again, so not reuse it. But it shows the price of the first IL code compilation emission. Then we have one where we reuse the one that is compiled. So it's the first one has a hit, every subsequent one is super fast. And also, there is a generator for regex, which is now not creating this regex logic, not at runtime, but actually at compile time already. This generator is included since .NET 6, 7, 8. I'm not sure anymore, but definitely in .NET 9 and .NET 8. And we can take a peek. If I hit F12, we again see we are in some generated document. Whenever you see in your IDE a .g.cs, there's usually a hint that this is a generated document. Or we also see auto-generated here. And this is the regex that is emitted by the regex generator. We could take a look at how regex is implemented under the hood. All in C# code, there is no IL code, which means we can compile this regex at compile time already, and we do not pay the first price, the IL price, at runtime. So what's the performance difference of this regex? So the first one, a bit of a baseline, will be the interpreted version. Well, we create the regex every time, so we have a bunch of application. But this is like the runtime, roughly the runtime of this interpreted version. If we use the compiled version, this is what I meant with the noticeable impact at the first one. But every subsequent one will be super fast. So if we use a regex more than once, then definitely use the compiled version. Now with the generated version, it's even slightly faster, but this is quite neglectable. We are here in nanoseconds area. But the cool thing is we do not pay the price here for the first compilation. So with the source generated regex, we don't pay this price for the first one. The first invocation already is as fast as possible. Now keeping this in mind, so when we have now in AOT, when we take a look at the implementation of regex, let's jump to the constructor and follow the constructor chain. Sooner or later, we will hit this segment where it says, is the compiled feature set? Is the compiled feature set? And also, is this code dynamically compiled? Which is the .NET wording for, is the just-in-time compiler available? Can we emit new IL code and emit this compiled, that one-time compiled version of the JIT? If we don't, we fall back to the interpreter. So if we were using the compiled regex in an AOT scenario, we will always have the interpreted version of it. So we would have a bit of a performance impact here with regexes, which could show up in your profiling. But if we use the generated version, since it's already fully done at source compile time, nothing to do at runtime, we have performance even in AOT. Now, where do interceptors come into this scenario? Let's take a look at this minimal web API project. I created this by firing up my terminal and say .NET new Web API AOT, which is now creating a minimal Web API application that also has publish AOT set to true. So when we publish this, the AOT toolchain will be invoked. Additionally, this doesn't work out of the box with just the .NET SDK. You also need some C++ and linking workloads installed for the relevant target machine so that it can publish for AOT. In this web application, I log the initial start timestamp and also when the application has started. So when this web application is ready to receive requests, I just log how long did it take for this application to start up to be ready to receive requests. Then the rest is very much from the example where we have two map gets, one which is listing all of the to-dos and one that is listing the to-dos by ID. There is already source level interception going on in this project just by creating it from the template. I want to show this by disabling publish native AOT, yet still enable both the trimming analyzers and the AOT analyzers. Those are analyzers that come with the .NET SDK that warn if you use certain features in a scope where you promise that this may be used, or not promise, but you indicate that this may be used in AOT. For example, if you have a library and you want to make this library AOT compatible, you could enable the is AOT compatible flag, or you enable these analyzers individually so that you can say, okay, my library is Native AOT friendly, or you see where the warnings are and maybe try to fix them. Because, again, when we publish to Native AOT, we always trim. Trimming cannot be disabled, so it's trimmed aggressively, which means we could lose some of our code. Well, the trimmer is following all of our source code and all of our invocations, but what if we use code indirectly via reflection? Maybe we create a type via reflection. Maybe we invoke a method via reflection, or we load a new assembly. This is all not possible at runtime. This is not possible in native AOT scenarios. So during trimming, we may lose some code. And yeah, with AOT, there is no JIT, so we cannot use just-in-time compiler features. So if we enable these analyzers, but disable the publish AOT actually, so just saying, is this application Native AOT friendly? We do get two warnings at the map gets. And these warnings say that this method is attributed with requires unreferenced code, and it may break functionality when being trimmed, which is true for a native AOT application. But also, this map get requires dynamic code, which may also break in native AOT. Because what this map get is using under the hood, it's heavily using reflection and reflection emit, again, to emit special case delegates, special case request delegates for our map gets and map posts and all of our maps here. So if we were to publish this for AOT, we would be in trouble. But this is where this publish AOT comes in. When we enable that flag and actually do publish for native AOT, in ASP.NET Core, there is a generator for that. So again, if we go to the dependencies, check our target framework, go to source generators. In Visual Studio, the experience is very similar. Here we have the request delegate generator kicking in. And this request delegate generator, if it would load, okay, perhaps I need to build. There we go. Again, this is an auto-generated document generated by a source generator at compile time, at Roslyn compile time. Emitting this attribute, we see this is now actually using the new version of the attribute, because I'm on the latest .NET 9 SDK. If we were using earlier versions before .NET 9.0.2, you would still see the older version being emitted. But now with the new, with the latest SDK, actually no, excuse me, since 8.0.2, 400 or something. This new version is used, but since the .NET 9.0.200 this is now stable, and this version 1, when we use version 1 here, this will be supported for the future. And then for my 2 map gets, 2 interceptors are emitted. This is the first one, called map get 0. If we were to understand and decode this encoded string, we would exactly be mapping to our map get invocation here, and the other map get invocation, if we scroll down to the second interceptor, is now map get 2. Again, intercepted the call. And this is now avoiding all of the reflection emit, so that we can actually use native AOT without changing our code. Because that's the cool part of interceptors. The source generator author needs to take care of how to create this special case method, then intercept the user calls that would have, because we're still calling here, from a source code perspective, we're still calling this method that is actually annotated with it requires unreferenced code, so some reflection may be going on, and also it requires dynamic code, so new code will be emitted at runtime. But we don't get any warnings because the interceptor actually has, the generator has emitted an interceptor, so at runtime this will not be called. If I do a breakpoint here, we would never hit this. And with that, we can use native. This is how the .NET team with interceptors enabled native AOT for ASP.NET Core minimal APIs. Now I want to show you the benefit of native AOT with this, with the better startup performance. So I compiled this version of the application twice. Once we're using the just-in-time, so this is IL code, that both have been trimmed. I really thought this was a fire alarm. Which also uses trimming, compiles it to a single file, and is framework is not framework dependent, but self-contained. Just to have the similar experience, because this is all what native AOT is doing. It uses single file deployment, single file publishing, trimming, and also emitting it in a self-contained fashion. So at the target machine, we do not need the .NET runtime to be installed. And if we launch the JIT version, now again, this is a very small demo web application, so startup is still super fast. It takes roughly 500 milliseconds. And we could hit this endpoint and get all of our to-dos. Also, yeah, I need to go /to-dos, because this is what we map to. And all is working. So after 500 milliseconds, this just-in-time compiled application is ready to receive requests. If we jump to the native AOT version, this will only take 30 milliseconds. Or in this case, 35 milliseconds. Because there is nothing to be compiled at runtime. It just starts the code, and the startup is as fast as possible. But there is no JIT, so some features may break, some features may not. And for the features that do break, not every scenario that is working in the .NET in the .NET ecosystem with the common just-in-time compiler toolchain is working in AOT just yet. But with the source-level interceptions, without changing any of our user code, the tooling could more and more introduce interceptors that makes our code still work in native AOT scenarios. Now, mentioning that, it's not necessary that AOT is always better, because if you need quick startup, or startup is as fast as possible, then native AOT is the way to go. As I mentioned, the JIT compiler really is a beast, because the JIT compiler is at runtime analyzing our code, instrumenting the code that is running, and potentially then improving our code at runtime. Like maybe we call a generic method only with a specific type or a specific scenario all the time. Then the code is basically self-optimizing it the more it runs. So for if you don't need a super quick startup, then the JIT is perfectly fine. But in super high scaling scenarios, AOT is amazing. And the startup performance for this super simple demo app is measurable. So with your larger applications, this impact may even be larger. I mentioned that there are quite a bit of limitations with native AOT, also listing the documentation, and there is also a feature table with .NET 8. A lot of stuff was still experimental. With .NET 9, a lot of scenarios are supported already, but not all of them. So depending on the framework, depending on the libraries that you're using, they may not be working yet, but over time in the ecosystem, we will get more and more generators that emit more and more interceptors, and then our code will just work without needing to change our user code. Now, I would like to take a brief peek at how to create a generator that is emitting this code. I want to take a peek at the generator I showed earlier, which is invoking interceptors for this enum get name, and enum is defined. Now, this is not a source generator talk. There is a lot of intricacies when it comes to building a source generator. I'm just pointing out the portions that are interesting for source level interception. So what I'm searching here is so-called invocation expressions. This is basically when we have a dot. We have an instance dot member, like a property or a method, or a static type dot a static property or method or field. Those are invocations. And for these invocations, we basically find, is any of these invocations this enum.getName or enum.isDefined? And in case it is, we now use the Roslyn API to get an interceptable location for us. So we know the invocation where our enum.getName is called, and we receive the interceptable location type. This has now been added in the later versions of Roslyn. And this one, if we take a peek at this, we will see very familiar data, the int version and the string data, which I need for this attribute to be filled. Then we go on with our generator, and when we actually emit our C# code, generator is just writing out C# code, we will then use this interceptable location and call this getInterceptsLocation attribute syntax, which is an extension method that just returns this attribute that we need to put on the interceptor with all its data filled, with the version filled, and the data filled. So that we get, when we compile our application and go into the example and actually taking a peek what the generator is emitting. Now, first of all, again, the generator, since this attribute doesn't exist in the BCL, and this attribute, and since generators cannot depend on other generators, every generator should emit this attribute for itself. And we do this with file scoped types so that we do not mess with other interceptors. And then we just start attributing our interceptors that have, again, the compatible signature. And exactly this line, we have the global system one to compile service intercepts location attribute with the data, with the version and the data. This is what we get from this method. To complete the session, I want to talk very briefly about the history of the C# of the Roslyn compiler. So what the Roslyn compiler is, the cool thing, is just a library. So you could build your own tools that use Roslyn. When you do MS build or when you do .NET build, invokes MS build, which eventually invokes Roslyn. So there's various hosts of the Roslyn toolchain. And since Roslyn 4.10, which is included in this in 8.0.300 SDK, we get interceptor method, with which we can understand which method is the interceptor. We have an interception going on, and with this shows us here is the interceptor, no longer the original method. And we got those new types that we showed in the later version that have this version data and also this extension method. In earlier versions, they were attributed via the experimental attribute, so this was still experimental, but now since Roslyn 4.13, which is included in the .NET 9.0.200 SDK, so the version that just got released a month ago, interceptors are stable and free for the ecosystem to use and to depend on. The last statement, with great power comes great responsibility. When you have an interceptor, don't change the expectations of your application. Don't do something different. The behavior, the business behavior should not change, or the technical behavior should not, the business behavior shouldn't change, but the technical implementation may change. So for example, instead of using IL emission, use directly compiled code. But don't change the behavior. You may get flagged. Your package may get flagged. With that, this is the QR code that is linking to my repository. I listed all the demos if you want to play through them yourself. I also have a bit of a textual presentation where you could go through and experience interceptors and source generators for yourself. Oops, I still see cameras. And then going to the final slide, to please wait this session. I would heavily appreciate your feedback. Let me know what you liked. Let me know what you disliked. And so there's just one last thing to say. Heel erg bedankt voor het luisteren. Veel plezier nog op FutureTech. Tot ziens.